Okay, so last week we introduced the recursive based filtering technique as one scheme for doing state estimation. And the key idea was that we were always interested in estimating the current state of a system given new observations and new controls, exploiting the previously computed belief. So the goal was, using a belief at time t-1, how can we evolve the belief so that we obtain the belief at time t, taking into account the most recent observation and taking into account the most recent control command. This was kind of the task that we looked into from a general perspective of the base filter, derived the basic base filter ring equation, and this will be the starting point for today. And then we looked into some typical models for sensors and for motion. So we don't dive into the details of how motion or how sensor data can be represented here, but instead we look into the core framework of the Kalman filter and how it can be applied for recursive state estimation. And then next week we will look into one application of the extended Kalman filter for estimating the position of a sensor and landmark locations in the environment. So very similar to what we've done in bundle adjustment. So we can introduce the Kalman filter again with the idea of recursive state estimation, and we can take an example, let's say, with ships. So we are a ship which is currently here at that position with some uncertainty involved maybe. And so the question is, where are we going? And we are sailing at night and it's very hard to see anything. So basically sailing more or less blind. So one of the things we can do, we can, by that reckoning, based on the speed that we sail and the direction we are sailing to, can estimate where we end up, let's say, half an hour later. So we may up having this estimate. So we should be somewhere over here, just taking the distance we are sailing to, the approximate speed where we are sailing, but not taking into account any observation. So this is something that is the prediction step. So we're taking into account the current information that we have from odometry or taking the time and the speed estimate that we have to evolve the state. So this is kind of the prediction step of the Kalman filter, or of the base filter. Okay, what we then do is we look to the land and we see a lighthouse over here. So it's very dark, so we see just a lighthouse over there. So you say, oh, there are two lighthouses over here, so it's very likely to be this lighthouse. And then I can estimate where I should be given this observation. Okay? So then the next thing. So we take the map that we have and say, okay, according to the observation, so I'm observing this lighthouse over here. This is my observation. I can use this to estimate my location. What I then can do, I can estimate, my location according to my observation. So if I only have this observation, that would be the best estimate for my position. And now I have kind of two things. The first thing is I have a prediction where I think I am based on the speed that I was traveling. This was kind of the black cross. And I have an estimate where I should be according to my observation, the green cross over here. And then the question is, how do I fuse those two estimates? If I have this as two probability distributions with different uncertainties, because there's an uncertainty involved in doing this observation of the lighthouse, and there's uncertainty, let's say, in the direction where I was sailing to, and the speed measurements, I will have to fuse those beliefs and will probably end up with something like the red thing over here, which is the estimate taking into account the previous pose, my prediction, my observation, and this gives me my corrected estimate. And these are exactly the steps of the base filter, and the Kalman filter is a special variant of the base filter to do this state estimation. And these slides actually quite nicely illustrate all the things which we will encounter now. So the prediction step, estimating where we are at the next point in time, not taking into account any observation. Then we obtain an observation. We say, what are we observing? And based on that, we get an observation which tells us we should be actually somewhere else. So this is actually what I should observe, my predicted observation, and this is where I am according to my observation. And then I fuse those beliefs within something which is called the correction step in the Kalman filter to obtain that red estimate. Okay, so the basic idea is clear behind the steps. So we have the prediction step, we obtain our measurement, then this leads us to the correction step. Okay, so this is basically where we stopped with the base filter last week. So this was the equation for the prediction and the correction. So again, the predicted belief, the belief with the bar over here, at time t. Predicted belief means not taking into account the observation. We are just making the prediction according to the controls. And we started here with the belief where we have been at the previous point in time, so the belief at time t minus 1, and how the state evolves. So how do we go from t minus 1, given the control command ut, to my new pose? So in the example before, this command could, for example, been sail straight forward for half an hour. This would be the control command. And we say, okay, given where we know where we've been before, and this command, we know where we should end up with. We have the integral over here because we don't exactly know where we've been before. This is a belief, so we have to iterate, so kind of check all possible states of the probability distribution over states. So if this is a Dirac distribution, that means we just perfectly know the state we are in, then just this probability distribution remains, because then it's just propagating forward from the exactly known starting location. If this is a Gaussian with some uncertainty, this step will basically increase the uncertainty, like a convolution, or Faltung in German. So the uncertainty of the motion will be combined with the uncertainty of the state that we had before. This gives our predicted belief. So the predicted belief typically has a larger uncertainty than the belief we had before. Because we just say, give a command, sail for half an hour in the forward direction. If everything works out perfectly and I perfectly execute that command, and I know that I can perfectly sail for half an hour in perfectly the right direction, I basically maintain the same uncertainty I had before. But typically I make some mistakes. Maybe I'm not going for half an hour, maybe just for 29 minutes and 50 seconds, or maybe I'm slightly by a small angular mistake where I'm sailing to, or there are some currents or whatever, so my uncertainty increases. And so the overall uncertainty of my predicted belief is larger than the uncertainty I had before. So this was the prediction step. And then the correction step, we take into account the observation, that is this expression over here, and combine it with the estimated belief. And the Gauss, what the Kalman filter now does, it says, okay, our world is Gaussian. Everything is Gaussian. It says, my belief is a Gaussian distribution, so my starting belief. My motion model, so how the state evolves from time t minus 1 to t, given the control command, is Gaussian. And it says, and my observation are Gaussians. My observation model is Gaussian. And then we will show that this turns into a new Gaussian belief. If this is Gaussian, this is Gaussian, this is Gaussian, this will turn into a Gaussian as well. And this is what the Kalman filter exploits. So it says everything has to be Gaussian. It's the key assumption of the Kalman filter. And it will make some additional constraints on those two models over here. Basically, these are linear transformations. So what the Kalman filter is, it is a base filter. It's one implementation of the general framework of the base filter as it implements those two equations over here. And it is made for the linear Gaussian case. So we only have Gaussian distributions, and all models involved are linear models. That means for the motion, as well as for the observation. And under these two assumptions, that everything is Gaussian, and that everything is linear, this is actually the optimal estimate that we are going to obtain. It's an optimal estimator. You can't do better if you live in a Gaussian world and you have only linear models. Of course, all your observations are independent of each other, and under these assumptions, this is the optimal approach that we can take. So there's nothing better if everything is Gaussian, everything is linear, and everything is independent of each other. Although that's typically not the case, and that's the reason why we typically don't end up using the Kalman filter in the end, but we have extensions of the Kalman filter that is, for example, able to deal with nonlinearities, which is something that we typically experience. Okay? So we live in a Gaussian world, so everything looks Gaussian in all these distributions. Don't have to go into details. And we can use this to estimate a one-dimensional state, can be a multiple-dimensional state, but that's the way that the Kalman filter works. So everything is Gaussian. Okay, now we have Gaussian beliefs. All models are Gaussians. So we have to evolve our belief from time t-1 to t in this Gaussian world according to the motion or the controls and the observations that are obtained. So the question is how to update my belief according to motions and according to my observations. Okay, so two properties are key that are exploited in the derivation of the Kalman filter. So the whole derivation of the Kalman filter can be quite involved. So we'll just take out some key snippets to show certain aspects of that. I don't go through the full derivation here. But two concepts are important that we are going to explore. This marginalization and conditioning of Gaussian distribution. That's something that we need. So what is marginalization? What is conditioning? So if we have a random variable which can be split up into two components, so they can be one-dimensional, they can also be multi-dimensional. And I know that the whole state vector is distributed according to a Gaussian. So this probability distribution P of x is a Gaussian, the mean covariance matrix. Then I know that the marginal distributions are also Gaussian. So that means the distribution only about P of A, not taking into account P of B, is a Gaussian, and the same holds the other way around. The distribution about P of B is also Gaussian. So that if I can marginalize out XA or XB, so in this case I marginalize out XB, in this case I marginalize out XA, and they are both Gaussian distributions. Okay, so I can take a part of the state space and I only look into the probability distribution of this part of the state space. The second thing which is important are the conditional distributions. So how can I estimate P of A given I have knowledge about B? So this is P of A given B. And it turns out also these conditionals are Gaussian distributions. So P of A given B, so given I know B, I can estimate A potentially better. Maybe, maybe not, but depending if these parts are independent or not, I may be able to estimate that the Gaussian distribution may look different. Right? If they would be independent of each other, would be the same as the marginal, but often they're not independent of each other. The important thing is this is a Gaussian distribution as well. And it doesn't matter in which order they are. It holds for P of XA given XB or P of XB given XA. So these are also conditional distribution. Okay? So how does this marginalization look like? If this is our state space about these two variables P of XA and P of XB, which is Gaussian, then we have a mean vector which we can split up into a mean about A and a mean about B, and we have a covariance matrix which can actually split up into four parts, four matrices, four submatrices here. If this is given, so we know the parameters of this Gaussian distribution about the joint distribution, so these are the parameters of the joint, we can directly obtain the parameters of the marginal distribution by marginalizing out XB in a very, very simple way. So if I'm only interested about XA, the mean is just this part over here of my distribution P of XA, and this is my covariance matrix. So I just need to cut out a part of the covariance matrix and I cut out a part of the state vector. So P of XA, which is this distribution over here, has these parameters. So that means using a Gaussian distribution in this moment form means that I use the mean and the covariance matrix to represent this Gaussian. Marginalization is easy. I just can cut out part of the state vector and can cut out a part of the covariance matrix, and I obtain the marginal distribution. Okay, so there's something which is easy, which can be done easily. Conditioning is a bit more tricky, a bit more complicated. So what I want to do now is I want to compute, I have the joint belief given with the same parameters as before. And what I want to now do is I want to compute P of XA given XB. So assuming I know the distribution about XB, how can I exploit this to estimate XA? So P of XA given XB is the joint distribution P of XA and XB divided by P of XB. And this is a Gaussian again. But the parameters of this Gaussian are now somewhat more complicated. And the key thing is, which introduces computational complexity in here, is typically this term over here. Because it requires us to invert this part of the matrix. So this is a high-dimensional matrix. So let's say we have a high-dimensional state space, and this is a small part of the state space. This is a large part of the state space. This requires an inversion of this matrix, and this may be computationally expensive. We can do it, but we may need to invert this matrix. But we can compute the conditional, and the important thing is that the conditional distribution is, again, a Gaussian distribution. So to sum this up, if this is our belief, our Gaussian distribution, we can split it up, or we can compute the marginal distribution and the conditional distribution. And if I stay in this moment form, that means I represent my belief through a mean and a covariance matrix, marginalization is easy, conditioning is difficult. So there's an alternative approach to represent a Gaussian distribution using the information form or the canonical form. We use an information vector and the information matrix. So the inverse, so in terms of information matrix, the inverse of the covariance matrix to represent a belief. You can do this equivalently. And then actually these things swap. Then marginalization becomes difficult and conditioning becomes more easy. So depending on what I need to do, there's one or the other form to represent a Gaussian, which may be more suited to do what you want to do. But so far we stay here in this moment form. So we use mean and covariance matrix to come up with an estimate, about our belief. And in this case, marginalization is easy and conditioning is difficult, or more difficult. Especially more costly because I have this inversion in there. So this part is expensive to compute, especially the inversion can be complex. Okay? So the next thing that we need are that we have a linear model for observations and for our motion. And so we start with the motion and say, how does such a linear model look like? So what does this linear model do? It tells me how I evolve the state from xt minus 1 to t given my command ut. And this should be a linear function. So that means, as we have it here, we have our new state at xt, which I compute based on the state at the previous point in time, plus my odometry command, or my information about the motion. Like this example, sail for 30 minutes into one given direction. So two things need to be considered here. The first thing is one matrix AT over here, and this matrix tells me how the state evolves without any additional control commands applied. So how does the system change the state on its own? And the second matrix B tells me what is the change to the state given the command that I'm going to execute. So this is a mapping, this matrix B, from the dimensionality of my control space, where the control commands or odometry commands are executed, into the state space. And this matrix over here maps from the state space into the state space, because it tells me how the state xt changes if no control is applied. And so how these two matrices look like typically depends on how your state space is represented. So one of the things is, let's say you have a very, very simple model where you have, you just want to represent, let's say, the XY location of a mobile platform. And if you don't emit any commands, so you don't put any current to the motors, what will the system do? A real platform standing there, you don't apply any control command. If you don't apply any control command, the system does nothing, just standing there. So in this case, this matrix A will be the identity matrix, because the state doesn't change. And then the command, maybe the current I put on the left and the right motor, and this needs to be mapped to the state space. This can be a bit more complicated, this mapping. Doesn't have to be, but can be. Now, what happens if I represent my state space slightly more complicated? Let's say I have not only the x and y location as part of my state space, but also the velocity in x and the velocity in y. So I have a four-dimensional. So if x, so this was for x equals whatever x and y location, and if my state space now gets a bit more complicated, x, y, x dot, y dot. So the velocities are here and there. So this is so kind of xy location. And these are the speeds in x and y. So what happens if I have my system and I have an x and y location, and part of the state space is also the speed, the current speed of the system. And I don't do anything. I don't change anything in the state space. So the command would then be, for example, setting an acceleration. How would this matrix A look like? Would it have the same form? Would it become more complex?
Speed is 0.
Doesn't necessarily has to be 0. So because the speed is now part of my state space, and then my controls is just an acceleration that I set to the system. So if the system is at a location going with 1 meter per second in the x direction, and I don't emit any acceleration to the system, it will drive as a constant speed, exactly. And how would, in this case, this matrix A look like?
On the diagonal, yes, and the speed is a constant. I don't know.
So there's a delta t. Let's say every half a second we emit this command, and there would be here twice 0.5 in there. So the delta t would go in there, because it maps how the speed will change the state. Because if I'm driving with the speed, I don't emit any control command, then this may differ. So depending on how my state space looks like, what I encode in there, and how my controls look like, this matrix A and B can be more easy or more complicated. Okay? Okay, the second thing, this was the motion model. And the second thing that we have is our observation model, which has this form. Let's call it like this, is computed as a matrix CT xt. What does this mean? This is a mapping from my state space through some magic matrix C into the space of observations. So from state to observation. And what this function C, or this matrix C, does, it computes something called the expected observation. So what would I expect to observe given I'm in the state xt? So given I'm in state xt, what is my expected observation? So kind of my mean observation that I would expect to get if I'm in that state. So this matrix C typically needs to know something about what I'm observing. So it, for example, needs to know the location of the lighthouses in the environment. It says, given I know where I am and I know to which lighthouse I'm looking into, I can actually estimate what I should measure. So this function maps from the state space into the observation space. And intuitively, it is the expected observation. So what I'm expecting to observe given I'm in this state xt. So is this idea of an expected observation clear? So let's say as an example, I'm a mobile platform, I have my great 1D laser here, and I'm looking to this wall over there. Let's say I'm moving on in a 1D world. So the only thing I measure is I measure the distance to the wall from my current location, and I can move in my 1D world. So this function C, this matrix C, needs to have the knowledge that there is a wall. And then I can say, if I'm here at that position and I measure this distance, this should be whatever, 6 meters. If I'm here, I should measure 6.5 meters. If I'm here, I should measure actually 5.5 meters. Because based on the current state I'm in, and based on where the obstacles are, we can compute what I'm expecting, what it's expected that I measure. Of course, there's measurement and noise involved in this, so my laser here is not perfect, but I get kind of the mean, the expected measurement. And this is exactly what this function C does here. Okay? If you look to the slide, there are 2 additional terms over here. And this is for the noise. So there's an additional noise in there. So this is supposed to be zero mean Gaussian noise. Okay? But the transformation itself tells me I have this function, I have this function, these 2 functions over here. So one is represented by A and B, and the second one by C. And these are linear functions, linear models. Okay, so this matrix A is an n by n matrix where n is the dimensionality of my state space, which describes me how I move from time t minus 1 to t without giving a motion command. So it's kind of how does the system, the state of the system evolve on its own. And the second matrix B was a mapping from, in this case, whatever, the L-dimensional observation control space to the n-dimensional state space, which basically tells me what do I need to add to this, how the state would evolve on its own, given that I emitted a command. So how does a command UT changes the state? What is the delta that's added or subtracted to the state, given the control command UT? And then we have the matrix CT, which maps from the n-dimensional state space to the k-dimensional observation space, because I'm mapping from state to observations, and describes what I'm expected to observe, what I'm expected to see. So it's the expected observation. So it's written here on the slide before, was written as ZT, but this is not the real observation that I obtained. This is kind of the predicted observation, what I'm expected to see. Okay. And then we have these 2 random variables, which represent the noise in there. 0 is this kind of an additive term with zero mean and zero mean Gaussian. And they have 2 covariance matrices R and Q. And they describe kind of the uncertainty involved in the control command and the uncertainty involved in the observation. At that point, so I think you hear about the Kalman filter for the first time, right? Did Heiner Kuhlmann already introduce the Kalman filter in his lecture? I guess not. Has he done it, yes or no?
We had the statistics.
Okay, so that's good. So you know a little bit about it. Heiner Kuhlmann will also do it again at some point in time, but we typically all do it in a slightly different way. The only thing you need to make sure this RT and QT, depending on the textbook you're using, is sometimes swapped. So don't get confused. In this lecture here, RT is the motion and QT is the uncertainty of the observation. Motion uncertainty, observation uncertainty. Some books swap it. Some do it this way, some the other way, just to not get confused. Okay, so now we have all the components for the mean and the covariance matrix for the individual models here. So we can actually use this to now specify how my Gaussian distribution looks like for the motion. So I said we live in a Gaussian. Okay. We're living in a Gaussian world, so we need to be able to write down p of xt given xt minus 1 and the command. We know it's a Gaussian distribution, but the question is, how does this Gaussian distribution actually look like? So this is my variable under consideration. So the variable my distribution is about. So we have kind of the constant term over here, and we said the uncertainty of this distribution is my matrix RT. So this is my the constant term of my Gaussian distribution. And now, how does this function look like? This is basically given xt minus 1. Where will I end up with? This gives me kind of the mean. And I have my variable x, and I know about the uncertainty. So what needs to go here? So I have my kind of x or xt, the random variable I'm interested in. And what is now the mean of this Gaussian distribution? What is the mean of the predicted belief? Or not the predicted belief, just of the motion model. So it's just the motion model, not the predicted belief, just the motion model. Yeah.
BT times UT.
Nearly. So it takes into account the whole thing. It's not only the BT. It takes the whole transformation into account. So it's A xt minus 1, or AT xt minus 1, minus BT UT, transpose, then my RT inverse, and the second term here again. Okay? So this is my linear motion model. So how does a state evolves? Given I was at xt minus 1 before, I execute the command ut, and I end up at xt. This is a Gaussian distribution, and this is how the Gaussian distribution looks like. So it's a Gaussian, and this is kind of the linear transformation in there. Okay? And the RT is the additional noise that the motion introduces to the system, to the overall system. So the uncertainty of my motion. Okay? So if this goes towards 0, it means I'm perfectly certain about my motion. So this matrix basically is a zero matrix, means I can perfectly execute the motion that I need to execute. Okay? Okay, so this is the equation that we have. Done everything correct? Yes, okay, perfect. Now we can do the same thing with our observation. P of zt given xt. How does this function look like? Again, determinant 2 pi. Know what goes there. So this is my observation of yes. Qt. How do we continue here? Zt minus Ct times xt. So given the pole, given the state, transposed Qt to the power of minus 1 Zt minus Ct xt. Okay, perfect. So this is the measurement noise of my sensor, the Qt, and the difference between what I measured in reality and what I'm expecting to observe. Because I know where I am, so I have an expectation about what I should observe, and I simply compare that to what I observe in reality. If it perfectly matches, I'm in the mode of my Gaussian distribution. The further I'm away from what I expect to measure, the lower the probability we'll get into. Okay, so we said, okay, everything is linear, and everything is a Gaussian distribution, all the components. And just because these functions are linear, everything actually stays a Gaussian distribution. So if you transform a Gaussian under a linear transformation, it stays a Gaussian. If this would be a nonlinear function, your Gaussian would not stay Gaussian. Right? If you map it through any arbitrary function, your Gaussian will not have a Gaussian shape anymore. So it's important that this is it's linear so that these distributions stay a Gaussian distribution. The next thing we need to show that actually everything stays Gaussian if we update our belief. You know, we have our recursive update formula. So how can we make sure that even if the individual distributions are Gaussian, that everything stays a Gaussian? So let's start with the last step. So the last step, the correction step, was my new belief is a normalization constant, my observation model, which is Gaussian, this guy over here, and my previous belief. So this guy is Gaussian. We perfectly know that. We have written it down here. So this is a Gaussian distribution. The expected belief, what we expect to end up with, we actually don't know yet, right? But let's assume it's a Gaussian. Let's assume that it's Gaussian, this part over here. If this is Gaussian, this is Gaussian, is the result Gaussian? Yes. Why? The product of two Gaussians stays a Gaussian. Right? So, if this is Gaussian, you can take the product of two Gaussian distributions and it will stay Gaussian. So the product of two Gaussian is again a Gaussian. So the main thing we have to show is this guy really a Gaussian distribution. Okay? Okay, let's look into the expression. How does this expression look like? This is this term over here. So we say, okay, this is Gaussian. We know that. Okay, so this guy is a Gaussian because we have specified it here, right? So this is a Gaussian distribution. And we said this is our recursive belief. So under the assumption that our initial belief is Gaussian, so once if we can assume that our initial belief is Gaussian, and everything else is Gaussian, this will actually stay Gaussian as well. It's kind of the recursive assumption. So if, let's say we in the first, in the time step 0 where I put in a prior belief in there, and assuming this is a Gaussian, then this is Gaussian, assuming that everything works out, the result, the belief at the next point in time will be Gaussian. So this is then Gaussian again, it's kind of recursive. So this actually, I can assume that it's Gaussian if my initial belief is Gaussian, so I initialize my filter. Even if it is 0 mean and a covariance matrix which is infinitively large, maximum uncertainty. If I don't know anything, I can still say this is this shape. Okay, so this is a Gaussian. The question is, if this is Gaussian, will this be a Gaussian distribution? Because I have this ugly integral in there. So this may require further investigations if this is Gaussian or if this is not Gaussian. In order to do that, let's first expand those two terms. So let's say, take this term over here and put this guy in there. And put in there the parameters of the previous belief that it's Gaussian. If I do this, so just a copy-paste and expanding the two expressions, I end up getting something like this. So I have my normalization constant, which I don't care about at the moment. It's just a constant. So this is what we had before, the belief at t-1 and the motion model, the integral over the previous state we have been in. And I just copy-pasted what I've written here in these expressions over here. And this is my previous belief. So this is the mean at the previous point in time that I estimated, and the uncertainty of my filter at the previous point in time. So these are kind of the parameters of my recursive belief. Okay. So what I can do is, okay, let's simply define a function L and put all the stuff in here into this function L. That's okay. I can define this LT, which looks exactly like this, and then this is my belief, right? So the only thing I've done, I've defined this magic L, which is a function which contains these two terms, and then this is how my Gaussian distribution looks like. Now the trick comes. It says, okay, let's take this term L and split it up into two parts. One part which contains the xt, and one which contains the part about xt minus 1 and xt. So I say, okay, I can split LT up into terms. One term which takes both parts into account, and one part which takes all the part of the state space into account which only depends on xt, but not on xt minus 1. Okay? So then I can just, okay, I simply take the expression I had before and copy these two elements in here. So this part now is independent from the integral because it only addresses parts which depend on xt. So I can move this part out of the integral, move it here, so integrate only over this term over here. So this part that ends up to be is my the distribution, the Gaussian parameters of my distribution. So this part is a quadratic form, has the form of a Gaussian distribution. So this is Gaussian. I still have this remaining part over here. And what you now can derive over a couple of pages is show that this term in the end turns into a constant, an additional constant for this Gaussian distribution. I don't go into detail because it would fill a couple of pages. If you're interested in Probabilistic Robotics books, page 46 to 49, you find the full derivation to show that this in the end just turns out to be a constant. So that's what I said. Don't want to show the full derivation over here, but I want to show you the key trick that you need to do in order to show that everything stays Gaussian. And now, this is a bit involved. A couple of derivation steps you need to do to show that this actually turns out to be a Gaussian distribution. But once this is a Gaussian, I again have the product of two Gaussians, and then I know that the predicted belief is also Gaussian. Okay? So in the end, what I have is this is Gaussian, This is Gaussian, this is Gaussian, so this is Gaussian. So everything stays Gaussian. Everything is and stays Gaussian. So I have all my Gaussian distributions over here. So the key thing that we have done so far is to say we have a Gaussian observation model, we have a Gaussian motion model. They are all linear. If they are all linear, we combine all the equations according to the recursive Bayes filter, we end up having again a Gaussian belief. So everything is and stays Gaussian. If the original models are Gaussian and we have the linear transformations over here, then everything stays Gaussian. And this is the key insight. We can now say, okay, what we can do now is we just need to estimate the parameters of this Gaussian. So what do the mean and the covariance matrix look like? Which basically involves computing the products of Gaussian distributions, and we have this kind of, again, product of Gaussians. We have this normalization constant somewhere in there, but that's what we end up with. And then we basically have products of Gaussians. There's different uncertainties, but they're all Gaussians, and we can actually combine them into, again, a new Gaussian, a new mean, and a new covariance matrix. So we'll do a 5-minute break at that point, and then we look how we end up obtaining the Kalman filter. Okay, so we have shown, or let's say better illustrated, that everything stays a Gaussian distribution. So the key question is, how do we represent Gaussian distributions typically? Because these are the parameters that we want to estimate for our belief at time t. So we want to estimate the representation of the Gaussian distribution at time t. And we do that with the mean vector and the covariance matrix typically. And so we have to do the same thing here. So from this update equations of the recursive Bayes filter, assuming that everything is Gaussian and linear, we need to estimate our new mean at time t and our covariance matrix at time t. Given we know the estimate at time t minus 1, we know these parameters and these parameters, and those we know, we had them on the blackboard. We have the previous belief. Now we need to say, what does the mean, what does a covariance matrix look like? If we now want to derive how they exactly look like, we need to exploit a few things. The first thing is the product of two Gaussians stays a Gaussian, as we have seen so far. Gaussians stay Gaussians under linear transformations. The marginal distribution and the conditional distribution of a Gaussian are still Gaussian distributions, and we need to know how to compute their mean and the covariance for the Gaussian and for the conditional case. We will have to exploit the matrix inversion lemma and have to do an exercise of a few pages of manipulating Gaussian distributions. Nothing is extremely complicated, unless that it's very likely that you will make some mistakes on these derivations. And this will, in the end, lead you to a very short algorithm which tells you how to compute the mean and the covariance matrix of the next step. That's how the algorithm looks like. And I will now go into the details and explain the individual steps which happen to obtain that. So what our input to our belief is, to our algorithm is the Gaussian parameters of the previous belief. So the previous mean and the previous covariance matrix, the motion command, and my observation. So this is the input, and the output will be the new mean and the new covariance matrix. These two lines over here are the prediction step. And these three lines are the update step. The prediction step is quite easy to see. So it says we have our mean estimate where we've been before. We have our odometry command. We have our linear transformation. So the only thing we need to do is we need to take the mean of the previous point in time and transform it under this linear model. And this will give us the new mean. So computing the new mean is as easy as that, just applying this linear transformation for our motion. Okay? So we say, we start at the previous mean that we had, and the odometry command, and via this function, this maps into the predicted mean, the predicted belief. Not taking into account the observation, only taking into account the control command. And then we have the uncertainty of this distribution, which is direct application of variance propagation or error propagation, which is the original uncertainty that I have at time t minus 1. I have this linear factor over here for A transposed, plus the additional noise which comes to gain through the motion. Okay? So and this gives us our predicted belief. So it's a combination of the uncertainty we had before, the transformation that we execute, and the uncertainty of the motion that we execute. So the transformation, this matrix A, so if there's, for example, the scaling involved, this would then scale this matrix over here. And so this is the uncertainty of the Gaussian under the the previous belief, transforming it, plus the additional noise that is added according to the uncertainty that is inherent to the motion. If you have perfect motion, this would simply be 0. But typically it's not 0 because our motion is never perfect. Okay? Then the line 4. So is everyone kind of happy with this, with the prediction step? It's basically taking a Gaussian, applying a linear transformation, and adding an additional noise according to the motion. That's what happens in these two lines. Okay, so the next thing is the computation in line 4 of the so-called Kalman gain. What the Kalman gain is, it's basically a weighting factor which tells me how much more should I trust my control commands, so the predicted belief, with respect to the observation that I'm going to observe. So if my motion is very certain and my sensor observation is very uncertain, I'll generate a Kalman gain which only trusts the motion. If it's the other way around, that my motion is extremely crappy, but I have the perfect sensor, this Kalman gain will be really small, and I will basically ignore the motion and will only take into account my observation. Typically, you're in between those two extrema. So you have an estimate about your motion, which has a certain uncertainty, and your sensor, and you basically combine them. And the Kalman filter, what it basically does, computes a weighted mean. And the Kalman gain tells you something about, is basically this weighting. And it depends on the uncertainty of my observation. So this is a key element in here. And it also depends here on the uncertainty from the prediction. So I'm basically weighing the uncertainty of my prediction with the uncertainty of my sensor observation. So if you think back about this first slide that I've shown with this landmark, the sailing example, we have these two lines, this green line and the black line. And the Kalman gain basically says, how much more should I trust the black line, or how much more should I trust the green line to end up at the red line? That's what it basically does. And then we compute the new mean as a weighted sum of the previous mean that we had, as the predicted mean, so the prediction, and the correction according to the observation. So what you can see here, so this is the real observation that we have, and this is the predicted observation. If they are equal, they're perfectly the same, this term will be 0, and I end up just with my predicted mean. So if at the position of the predicted mean, what I'm expecting to observe and what I observe fits perfectly, I don't change my mean. If there's a difference in here, then there's a certain innovation, it's also sometimes called, made to the mean estimate. So I kind of change it a little bit into the direction of where the observation tells me I should be. And then the last step, we have again an update of the information matrix, of the covariance matrix of the belief. Taking this Kalman gain into account, so this weighting between the uncertainty they had before, the uncertainty of the observation, and the weighting term in there. If we illustrate this by a very, very simple 1D example. So we are at some point, we evolve our state, and this is a prediction that we have, where we are, kind of 1D world. And then we obtain an observation of a measurement, which is this green curve, this green Gaussian distribution over here. And then I'm combining those two, this case ending up here with my blue distribution. And this takes into account the uncertainty of my prediction, the uncertainty of my observation. So here in this case, the observation has a smaller variance. And this gives me my joint belief. So I'm here in this example closer to my observation rather than to my prediction. But in the end, it's nothing more than a weighted mean. So I'm computing a weighted mean between my predicted belief and the innovation that comes, and the observation through this innovation. So how much should I change my prediction according to what I see? So we can again start from this point with the next iteration. So this is the current belief from the previous state. Then I need to make a new prediction. So I move forward. So let's say moved, whatever, 15, 18 meters forward, and it introduced additional uncertainty. There is a prediction where I am because my motion is very uncertain. And then I get another measurement, in this example, this curve over here, which is now not as peaked as it was before because this observation may be less certain. And then I actually fuse those. Sorry, yellow curve is probably very hard to visualize. Let's see. And this, I basically iterate those steps. So I always have the prediction step, the correction step, and the question is how much do I trade off prediction and observation? Just want to go back to the algorithm, make a short example of, just illustrate the extreme cases for having a very good observation or having a very, very crappy observation. So I have a high quality sensor and a low quality sensor. So what do we have? We have our Kalman gain, which is the uncertainty of my predicted belief, CT transposed, CT sigma bar T CT transposed plus QT inverse. And I had for the mean, the predicted mean plus Kalman gain ZT minus CT XT. Okay. So the example A is the perfect sensor. What does the perfect sensor mean in terms of those quantities? What does perfect sensor mean? So it's basically 0. Let's say if you have 1D case, it's basically 0. Okay, what does it mean? If this is 0, what it implies, so the Kalman gain simplifies so this term is 0 now, inverted, right? It simplifies to this term. If QT is 0, this guy is 0, we end up here. Okay? Everyone happy with that? Okay, let's simply resolve this bracket. This turns into xt bar CT transposed. So the individual terms swapped and inverted. So we have here CT transposed inverse sigma t to the power of 1 CT inverse. Okay? Okay. CT transposed times CT transposed inverted. So this is the identity matrix. Then my covariance matrix here times the covariance matrix inverted. Identity over here. So the only thing which remains is CT to the power of minus 1. So if you have the perfect sensor, that's how the Kalman gain looks like. Everyone fine with this? What does it mean if this is my Kalman gain? Simply compute the new mean. So this is the previous mean, the predicted mean that we have, plus Kalman gain, so CT to the power of minus 1, ZT, CT, XT. This turns into plus CT to the power of minus 1 times ZT minus CT to the power of minus 1 CT XT Where did I make the mistake? Oh, okay. Let XT have the predicted mean over here. Okay, so this term is again the identity matrix. And then I have plus predicted mean minus predicted mean. So they cancel out. The only thing which remains is this part over here, which is CT to the power of minus 1 ZT, which is the inverse of the function which computes the predicted measurement. So this now maps from the measurement space to the state space and takes the current observation that I have. So it computes directly the state from my observation. So basically says, where my sensor observation tells me where I am, I just put the state there because it's the perfect sensor. The perfect sensor tells me where I am, that's where I am. And this is exactly this result over here. So whatever I've done in the prediction doesn't matter at all because I'm not taking that into account anymore. I'm only using my observation to compute the state. Okay? So it's kind of at least illustrated. So if I have the perfect sensor, I'm ignoring my prediction. I'm setting my state into that state which would generate exactly my observation. So set myself in a state which would generate as the predicted observation, the observation that the sensor reported. Because the best thing I can do at that moment. We can also do the other case, which is we have the super shitty sensor. So bad sensor. What's the worst thing you can imagine? Yeah, exactly. QT towards infinity. Let's see what happens. We have again our Kalman gain. CT. Okay. If this is infinity, the sum of infinity and something else will give me infinity. I invert infinity. 1 divided by infinity basically turns into 0. If this turns into 0, the product of everything will be 0. So the Kalman gain will simply be 0. Okay? So if my observation has an infinitely large covariance matrix, the Kalman gain will go down to 0. So that's then easy. My new belief mean is the prediction that we had plus the Kalman gain plus something else. But Kalman gain is 0, so I will just stay with my prediction, which makes sense. If my sensor doesn't provide me any information, the best thing I can do is I stick with my prediction. Okay? So just add these two examples to at least illustrate you that this Kalman gain is something which makes sense. Okay, let's revisit a little bit the assumption that the Kalman filter does and see if they make sense, if they fit our real-world problems. So we said everything is Gaussian, linear models. So okay, let's say with the Gaussian world assumption, we may live for a while. For a couple of problems, that's not too bad. But what about these linear models? The key thing is, in most realistic problems, those models are not linear. My motion is often not linear. I typically have an orientation. So if I model a car has an orientation, and the steering angle matters. And as soon as you have angles involved, you have typically sine and cosine functions there, which are not linear. So you leave this linear world assumption. So most systems are actually nonlinear. That means we don't have this form here anymore. What we have is we have a more general form. It says the new state is given by the old state and the commands with some potentially nonlinear function g. And we have a nonlinear function h, which maps from the state space to the state of observations. Okay? What happens if we live in a nonlinear world, as we do, and we would squeeze our functions, our Gaussian distributions, through these nonlinear functions? Okay, so what we can see here is this is an input function, a Gaussian distribution with mean and covariance matrix. This is a linear function, a linear transformation. And if you want to say, how does this Gaussian look like transformed under this function, what we can do is for every value here, we can go through this function, map it to the y-axis, and get this function over here. Do this for every value. So like a small histogram, or infinitively small boxes. Just where this probability mass mapped to, and it will end up here. So this function maps this Gaussian into this Gaussian distribution. This is now a linear, sorry for that. This is a linear function. And we said under this linear function, a Gaussian stays a Gaussian. The Gaussian may change its shape. So it may have a new mean, a new covariance matrix. You can see that here. The variance even got smaller through this transformation. So this depends on this function a over here, on this scalar value a in the 1D case. So the parameters may change, but it still stays a Gaussian distribution. Now let's turn this function into a nonlinear function and see what happens. If we turn this function into a nonlinear function like this, and we do this mapping over here, the problem is that the resulting function has now this shape. And this is clearly not a Gaussian distribution. So even if you look to this function, you say, yeah, it's clearly nonlinear, but I can imagine birth functions. You're actually quite far away from your Gaussian. So that's the problem. What we have is if we allow for nonlinear functions here. If we allow for nonlinear functions here, the Gaussian is not mapped into a Gaussian anymore. I can still say, I don't care. Let's approximate this by a Gaussian. So if we would compute the first two moments from this distribution over here, we would end up with this blue curve. So the blue curve is actually the Gaussian represented through the first two moments computed from this distribution. But you can see a clear mismatch between the blue curve and the black curve over here. Okay, so the insight is nonlinear functions violate the, do not allow us to map a Gaussian through this nonlinear function and still maintain a Gaussian distribution. And in this case, the Kalman filter is not applicable anymore because the Kalman filter just uses a mean and a covariance matrix to represent its distributions. And again, this cannot be well represented through mean and covariance matrix. So what can we do? What can we do to resolve this problem? Any ideas? Yeah? I heard it somewhere.
We can linearize it.
Exactly. We can linearize our function. Standard approach. Non-linear function. I need it linear, so let's linearize it. So we can do local linearizations and linearize our function, and then use this linearized form of the transformation to compute the new Gaussian estimate. Linearization through Taylor expansion, rather straightforward. So our function g, which depends on the command and the previous state, where x t minus 1 is my variable in here, this is given, will turn into this nonlinear function evaluated at the previous point of the mean, where the mean was before, plus the first derivative, kind of how far I'm away from this, from the linearization point. So as we are living here in a potentially multidimensional world, we have to compute the Jacobians for this function g and the Jacobians for this function h. So the generalization of the first derivative. And then simply, how far is my variable x away from the linearization point? So just as a reminder, what is the Jacobian? The Jacobian is a matrix containing the partial derivatives. So the first dimension of the function g, so if this is my function, my vector-valued function, and so what you in the first row over here is always the first dimension of this function derived with respect to the first dimension of my x, second dimension of x to the nth dimension of x, and then we do this for every dimension of that function. And this is my Jacobian. So what the Jacobian describes is I have a nonlinear function like the green curve over here, or this surface. Then in this linearization point, this g describes a linearized form, so in this case here, a plane, and then I'm basically how far am I from this away from this linearization point, and this is my linear function. Okay? Okay, so these g and h, they need to be computed for every linearization point, so they differ for every linearization point. A truly linear function would have the same parameters everywhere, but I need to do this locally, so they depend on the linearization point, but they are again linear functions. So what I can do is I can say, great, I'm in a linearized world again, linear world through linearization. I can simply apply my Kalman filter again. Let's see how big the effect is. So this was the example that I had before. This was the problem that I have through my nonlinear function. What I now can do is I linearize the function. So the linearization of this blue curve is here the Taylor approximation, this red line. So I do this transformation under this red line, and I actually obtain this red curve over here, which is then the estimate that the EKF would use. So what you can see is clearly the red curve is far away from the real curve or the real distribution that I have. So I do a mistake by this local linearization. But at least I can linearize it and still apply my framework. I should always be aware that the more severe my nonlinearity is, the more my estimated distributions will deviate from the distributions I would obtain if the function would be truly linear. So it's clearly an assumption. Let's see how big the effect of this assumption is. So if I now increase the variance of this function here, so I have a larger uncertainty, that means the probability mass of this function will be spread further away from the linearization point, so from the mean, which is the linearization point. So more probability mass sits further away from my mean. This means more values will be mapped through the linear function, which is further away from the linearization point and likely to be worse from the approximation point of view. So this means, if I do this, the difference between the real Gaussian approximation of this function and what the Kalman filter would estimate, or the Taylor approximation, will differ, so this space increases. The difference between the blue and the red curve increases. If I, however, shrink my uncertainty, so I'm a very focused belief, all the probability mass, or a large part of the probability mass, will be mapped through this linear function near the linearization point, and then the quality is likely to be better. So if I kind of have here a Gaussian with a smaller uncertainty, like this one over here, those two functions actually will be very similar, and also the mistakes done through the nonlinear function are not that severe anymore. So the key thing, the key insight here is, the larger the uncertainty that I have, the more critical are the nonlinearities. If I have a very focused belief, the nonlinearities don't matter that much because they don't distort the distribution so much. Because more probability mass is concentrated within a small area near the linearization point. So, given that I have now my linearized form of my observation model and the linearized form of my motion model, what I need to do is I need to also specify the linearized motion model and observation model. So my linearized model still should be a Gaussian distribution as it was before. So I basically take exactly the same equation that I had before, but it's except of having here at times xt minus 1 plus bt ut, I simply have the linearized form. So evaluating the function g at the linearization point, and then I'm linear in xt minus 1. Wait. No, here. Linear in xt, sorry. Wait a moment, there is a mistake. So this should be xt, right? No. All fine. Sorry for that. Exactly. But we have the same thing, that RT still describes the noise of the motion that I have. The only thing which changes is here I have now the nonlinear form. And the same holds for the observation model. For the observation model, I still have the linearized form of the linearized observation model in here. A function h and ht. And qt still describes the measurement noise. So how do I need to fix my Kalman filter for that? I take my function, which I call now extended Kalman filter, and what I changed is here. This guy here is not expressed with a and b anymore, but through the function g. And here I don't have my matrix ct times the predicted mean, but I have my nonlinear function h and my nonlinear function g. So these are two changes. And what additionally changes, instead of my matrix A, I have the Jacobian, so the linearized form in here. And for CT, I have the linearization, so sitting over here, replacing CT by HT. The rest of the equation stays the same. So just use the linearized terms in order to compute the, it's called extended Kalman filter, extended in the sense that it can deal with nonlinear functions through linearization. But except of this, stays exactly the same as the Kalman filter. So the extended Kalman filter is nothing than a hack in the sense that it takes the Kalman filter, says everything which is nonlinear, I just linearize, put it back to the Kalman filter, here we go. Close my eyes and hope everything will be good. Of course, it's one approach you can do if you want to still apply your framework, but it is an approximation, and depending how severe your nonlinearities are, and depending how large the uncertainty in your belief is, the more likely your result will deviate from the true estimate of the probability distribution. But the true probability distribution may be very hard to estimate given these nonlinear functions. So what you can do with that, just in this example, for example, is localization. So what you have here, so this is an estimate where a platform is, and this is where we send it according to the control commands. So basically drive half a circle. So this is the dashed line. And then we have a couple of distinct points, so, or landmarks or lighthouses, 1, 2, 3, 4, 5, 6, where we know their location, and we observe them through our sensor. So while we are driving through the environment, so these are kind of the true positions where the system has been in reality due to inaccurate motion execution, and these are the observations where we see the landmarks. And they don't match the landmarks perfectly because there's measurement noise involved. And so what the Kalman filter does, it now starts with an initial belief and estimates a Gaussian distribution for the individual states. And so this is just the same slide we had before. And this is what you end up with. So this is your initial prior belief. This is where your estimate is. So you have a predicted belief and the corrected belief according to the observation. This is always the ground truth. You continue further. This is your prediction. This is the correction where you are. And you continue like this. And this is your, so the inner estimates here are always, so the dark gray estimates, the estimates according to the correction. And so these are the true poses, and these are the variances of the Kalman filter estimate. So we can take the same example and make our sensor more noisy. So this is exactly the image we had before. And now we have a more noisy sensor. You can see it, for example, here, here. So this Q is larger. The uncertainty of my measurement is larger. What you can see is if you now compare the results of this localization run and this localization run is that you have larger uncertainties involved in here. So those uncertainties of the estimate are larger. Also the predictions are larger. Any idea why the predictions are larger? If the sensor is more noisy, why are my predictions more uncertain? Exactly. So always the belief at time t minus 1 is already more uncertain. And the motion just adds uncertainty to this uncertainty. And therefore also the prediction gets more uncertain. That's exactly right. So therefore all the covariance matrices here are larger. Because with a more noisy sensor I cannot nail down the estimate as good as I could do it before. Okay? Okay, then we come to the end of the course today. What we've seen here is first the Kalman filter as one way for performing recursive state estimation in the context of Gaussian distributions and linear models. And then we extended that towards the extended Kalman filter saying, I have nonlinearities, I hope they are not too bad, so I just linearize my model and then use this linearized form for performing Kalman filtering. So basically, the linearized model say, I hope everything will be good, and I execute my extended Kalman filter. I obtain a Gaussian belief, although I know in reality this is not Gaussian anymore, will deviate a little bit from the Gaussian depending on my nonlinearities and my initial uncertainty that I had. But I say, I at least hope everything still is okay. And I can continue like that. So the Kalman filter works quite well. So it's a very popular technique which is used for recursive state estimation. And as long as my nonlinearities are not too bad, and as long as my uncertainty is not too large. So either I'm in a linear world and uncertainties can be as large as they want, it's all fine. But as soon as we're in a nonlinear world, the uncertainties are, the algorithm perform better if the uncertainties are small. So doing this term of local linearization is not the best thing you can do. Doing a Taylor approximation is just one option for doing that. And there are other alternatives on how you can do filtering. There are things like the unscented Kalman filter, which basically uses the unscented transform to estimate how the Gaussian would change under nonlinear function. What basically does, it doesn't take one single linearization point, but it takes distributes a couple of points, let's say, within the uncertainty ellipse, and then transforms all the points individually through the nonlinear function and computes again a Gaussian from the transformed points. There's one way to better cover the nonlinearities, and something was called the UKF, unscented Kalman filter, instead of the extended Kalman filter. And there are different variants of filters which are trying to overcome those limitations or improve the situations. We are not going to dive more into the details here. So we stick with the extended Kalman filter as one technique for performing this state estimation. The important thing is, as long as I'm in the linear case and Gaussian world, this is an optimal estimator. So what it does, it also minimizes the sum of the squared errors that you have. So it's completely equivalent to your standard least square solution. As long as you leave the Gaussian world, the linear world, as long as you leave the linear world, so you turn to nonlinear functions, then it actually deviates from the standard least squared approach you do via local linearizations. The reason is that the Kalman filter cannot relinearize. So you linearize your function once, you integrate into your belief, and you don't relinearize. The standard nonlinear least squares will relinearize at every iteration, and thus has the potential to perform better than the EKF in case of nonlinear functions. Because the EKF cannot relinearize. It never touches old observations and old controls anymore. So there's no relinearization involved. As long as no linearizations are needed, so no relinearization is needed, they are equivalent, both approaches. But as long as we live in a nonlinear world, they will provide different estimates through the inability of the Kalman filter to relinearize. Okay, that's it from my side. Again, the most intuitive description, all the notation, is in line with chapter 3 of the Probabilistic Robotics book. If you're interested in a derivation, also derivation in the book is quite well, but you may look into the second book with the Thrun and Winston on manipulating multivariate Gaussian densities, where they derive also the basic equations of the Kalman filter in the end. These are two recommendations for further reading if you want to dive into more details into that. That's it from my side for today. Is there any question I can answer at that point? Yes, please.
Why would you build 6 light towers as arranged before?
Why would I build?
Also am Bild vorhin
Yeah.
waren ja 6 Leute.
Okay, so these are not lighthouses. So I just said these are just landmarks. This can also be distinct feature points in the environment, something that you can observe with your sensor. So I just try to make the connection with the original example I showed in the beginning. So these are not necessarily lighthouses. These can be any arbitrary feature points, like SIF features that we detected in the environment where we know their location. Okay, any further questions? So if this is not the case, thank you very much for coming, and we'll see each other next week. Thank you.